I hope you can hear me at the back. My voice is usually very weak. Can you? Okay, so I would like to speak about strontium vanadate, electronic structure of strontium vanadate. So the driving force behind this work is Ray Sakuma and Philip Werner, who is sitting there. So I think Fujimori Sensei has already described quite a lot about the system, so maybe I'll just go very quickly. So this is supposed to be a prototype of correlated metals. It has a very simple cubic structure, so that is probably why it has been studied a lot in the literature. You can find a lot of papers on this. So our concern here is to study the electronic structure of the T2G band coming from vanadium. This is oxygen, and this is a typical electronic structure of this perovskite. So let me first give a little motivation for doing this calculation. So this is a comparison between the photo emission and base photo emission data with theoretical calculations. So the calculation here is done within the LDA and the GW. We can forget for the moment about the local GW. So we just look at the black and the red curves here for the spectra. So we see that quite a few problems. Of course, in LDA, we did not expect to get satellite features. So this is the incoherent features at around -1.5 eV, and there are also some incoherent feature here around 2.5 or 3 eV, supposed to be the lower and the upper Hubbard bands. So when we go from LDA to GW, we get some band narrowing, but it's not enough to explain the band narrowing in the experiment, which is, if you make an estimate from effective mass, it's about 1.3 eV. That is half of the LDA bandwidth. And also in our calculation, we do not found a lower Hubbard band, as you can see here, although we did find the upper Hubbard band in these calculations, in the GW calculations, and it's much too high energy. It's around 4 eV. So overestimations of a satellite structure in GW is a common problem of this theory, because this is a local, is a linear in W, so it tends to overestimate the satellite features. So I would like to show you some more detailed GW calculations. This is not our calculation. This has come from the recent paper by Gatti and Guzzo, where they made detailed comparisons between LDA and GW here. So if we first concentrate on the T2G band, so the calculations is essentially agree with our calculations. Get a still too large bandwidth compared to experiment, and they have also done a kind of a self-consistent calculations in GW, and there is essentially little effects on this for this system. For the oxygen band, the GW seems to improve the positions of the oxygen band. So the LDA band tends to be too high compared to experiment. So GW band, if you do the GW calculations, then it lowers the positions of the oxygen band. So there's still this problem with the band narrowing. So they have actually gone further. So they have included the so-called cumulant expansions in these calculations. And they do improve the descriptions of the high energy satellite. So this is the high energy satellite. So it decreases going through to to get a much lower energy. But the descriptions of the quasi-particle band is essentially unchanged when you go from GW to GW plus the cumulant. So there is still a problem in the bandwidth of the system. Let me give another example to describe the problem with the GW. So this is calculations of the spectral functions for the cerium alpha and gamma. So these are just two phases of cerium with the same structure but different volume. So the gamma has a larger volume. If we compare the two spectra, we see that there is a drastic reduction of the quasi-particle weight around the Fermi level when we go from the alpha to the gamma. And if we do GW calculations for these two phases, we essentially did not see much difference apart from a slight band narrowing, a little band narrowing when you go from alpha to gamma. And that is one can explain that from the fact that the gamma phase has a larger volume. But otherwise, there is no drastic reduction in the quasi-particle weight. And also, if you look at the satellite feature, the GW spectra tends to, again, to overestimate the satellite energy. So one would then like to add the vertex corrections on top of the GW self-energy to improve the descriptions of the spectral functions. So this is LDA plus DMFT calculations for the cerium. So this is the experimental spectra, and this is the calculations. So LDA plus DMFT appears to be able to describe this drastic reductions in the quasi-particle weight around the Fermi level. So the MFT captures the correct physics of this system. So, and what we would like to do then perhaps is to make combinations between GW and DMFT to be able to describe the electronic structure of strongly correlated systems. Now, DMFT is a local self-energy. Recently, we have found that the K-dependent self-energy can be important. So this is the calculations for within the GW approximations for this strontium vanadate, where we study the effects of the non-local self-energy on the quasi-particle band structure. So this is a comparison between the LDA and the full GW calculations, which is the red one, and the quasi-particle band structure that we get when we neglect the K-dependence of the self-energy. And we found that if we neglect the K-dependence, it tends to overestimates the band narrowing. And, so you can see here that the bandwidth decreases from 2.1 to 1.2. So this one could understand by realizing that the effective mass depends on two factors. Depends on the frequency dependence of the self-energy, as well as also on the K-dependence of the self-energy. So there are two terms in the effective mass. So this means that if you neglect the K-dependence of the self-energy, then essentially you just get a band narrowing coming from the Z factor, or the renormalization factor. So this is consistent with this picture here, because the Z factor for this system is about a half. So that is approximately what we get when we go from LDA to GW local. So that's about 1/2. So the message is that the K-dependent self-energy tends to widen the bandwidth. And this appears to be the case also when we do ion. This is a comparison between the LDA and GW with also the local component of the GW self-energy. So we get quite a significant band narrowing when we only consider the local part of the self-energy. So in fact, if you do GW calculation, there is very little difference between the LDA and the GW band structure. So now I would like to describe a little bit about this scheme where we combine the GW self-energy and the impurity self-energy from dynamical mean field theory. So this is quite an old work, already 10 years. It's done with collaborations with Antoine and Zilke in the audience. So the basic idea is rather simple. So if we consider a lattice, we will try to describe the local self-energy using dynamical mean field theory, because we know this is good to describe the local correlations. And the intersite or non-local self-energy we will describe within the GW approximations. So the idea is that non-local self-energy should be relatively much weaker compared to the local self-energy. So that is hopefully can be described in terms of perturbation, many-body perturbation theory, which is what GW is. So we get the local component of the self-energy is taken from DMFT and the non-local one from GW. So we would like to describe this in a more rigorous way. And this can be done using kind of generalizations of the Luttinger-Ward functional, where one also include not only the Green's functions, but also in the screen interactions in this energy functional. So the main quantity that we would like to approximate is this functional here, the psi, usually called the psi functional in this scheme. So that corresponds to the phi functional in the original Luttinger-Ward functional. So what we do here is we could split this functional psi into two components, off-site and the impurity, the on-site. So again, we use the DMFT for this on-site and GW for the off-site. So the GW psi has quite an explicit form. It's given by this diagram or the trace of GWG. And from this, you can then calculate the self-energy by taking a functional derivative with respect to the Green's function and the polarization with respect to the W. So for the impurity, we don't have an explicit picture, so because this is done usually using Quantum Monte Carlo, so we don't have any explicit form for the functional. And the main feature of this scheme is that we could take into account the double counting properly. So when we add the two self-energy, the GW self-energy and the impurity self-energy, there's an overlap between these two self-energy. That is the local part of the GW. It's already contained in this impurity self-energy. So what we have to do is then we have to subtract the local component of the GW self-energy. So this is this part here. And we have to do the same for the polarization. So with that, this scheme then generates additional self-consistency conditions. So this is the original self-consistency conditions in DMFT. And in addition to this, we have a new self-consistency conditions for the screen interactions, where we require that the local projections of the screen interaction should be equal to the screen interactions of the impurity. So these are the impurity Green's function and the impurity screen interactions. So the picture is that when we solve the impurity problem with a certain Hubbard U, this Hubbard U is screened within the impurity model in such a way that it is equal to the local W that you obtain from the full lattice. So I don't have much time to describe all this in detail, so I just go very quickly. So the self-consistency loop, in this we have not applied this self-consistency loop, but anyway I will try to describe it. So one start from the impurity problem. So given the G and the Hubbard U is now a frequency dependent U, one could calculate the self-energy of the impurity and also the screen interaction. So the next step is then to combine this with the GW self-energy. Just add the two and subtract the local component of the GW to avoid double counting. And then one check the self-consistency condition. Calculate the G local and the W local. And if this is not satisfied, then we calculate the new Weiss field and the new Hubbard U and continue. Now this scheme is, the full scheme is very complicated. In fact, I have neglected another loop for the GW part. So we have also a consistency, self-consistency loop for the GW. So we have to modify the Green's function in the GW self-energy, as well as recalculate the new screen interactions with a given G, a renormalized G, but we haven't shown it here. So obviously this scheme is very complicated, and it is not even clear if this is a good idea to do. So what we have done so far is to fix we start from a one-shot GW calculations and then just add the impurity self-energy on top of this. So actually, as I mentioned before, this scheme has been around for quite a long time, but we have not been able to properly implement it. But recently, there is a very important advance in the in solving the impurity problem with a dynamic U. So as we mentioned before, in this GW+DMFT scheme, the Hubbard U becomes a frequency-dependent quantity. So one would like to solve the impurity problem also with a dynamic U. So numbers of years ago, this is possibility now to solve the impurity problem with a dynamic U, with the work of Philip Werner and Ander Milles, and also of Rubtsov. These are kind of two complementary schemes with a strong coupling approach based on hybridization, expansions, and weak coupling limit. And also there is a kind of approximate method that was developed by Silke's group. So we have actually done some LDA plus DMFT calculations. So there is no GW here, just to illustrate the effect of the U, dynamic U. So this is for one of the pnictides. If you look at the spectral functions and make comparisons between the static and dynamic U, so one could see a significant band narrowing coming from the frequency dependence of the interactions. So this Banner is actually mainly come from the renormalization factor rising from the high energy part of the screen interaction. So we have not included the K-dependent self-energy in these calculations. It would be interesting in the future to add the K-dependence also in these calculations. So maybe I should skip that one. So I would like to describe a little bit about this scheme. And in particular, we have to worry about the double counting term. So in this kind of simplified scheme, where we just do a one-shot GW and add the impurity self-energy on top of the GW. So both of these calculations are based on the LDA. Start from LDA band and calculate the GW self-energy and also the impurity self-energy starting from LDA, and just combine the two self-energy. So this is the non-loop, this is the GW self-energy, and this is the impurity one. But then we have to subtract the double counting term from the GW component. And this double counting term has the following form. So we have to calculate the local Green's functions and the local W. So this self-energy corresponds to the impurity self-energy within the GW approximation. So if you would like to see how the U looks like, I have shown this before. So this is how the dynamic U looks like, this imaginary part and the real part. So we have a strong plasmon excitations at around 16 eV or so. And this is the real part of the screen interaction. So what I would like to show now is the result of the calculations. So we focus mainly on the band structure and the spectral functions around the Fermi level. So we have not studied the oxygen band and the other unoccupied bands. So we are mainly looking at the T2G band here. So this is our main result. So we make several comparisons here. So this is the LDA, the dot curve. So as you can see, it has a large bandwidth, about 2.6. So as I said before, the bandwidth estimated from effective mass is then about 1.3. So if it is, because the effective mass is about twice what you get from the LDA. So now if we go from LDA to GW, we see some band narrowing. So go from 2.6 to 2.1. So this is still significantly larger than the experiment. And we do just a DMFT calculations, but with a dynamic U. So this is a dynamic U calculations, not with a static U. We find we had a much more band narrowing. Yes, this is the green one. So in fact, it is kind of overestimates the band narrowing if we compare with the experiment. So when we add the GW self-energy on top of the DMFT self-energy, so we add the non-local component of the GW self-energy on top of this impurity self-energy, we get a band broadening, which is in agreement with what we had before within the GW approximations. So we seem to get quite a good agreement with this experiment. So if you compare this photoemission data that Professor Fujimori just showed in the previous talk. So the bottom of the band here is around minus half dV, so this agrees quite well. Unfortunately, there is no data for the unoccupied linear, but has a form what should I say? It's a curve. It curves around the Fermi level. So you get this skin structure. It's actually very weak. So it's almost no structure at all. Okay. So here I made a plot of the self-energy to understand better what happens. So these are the self-energies at two K point, the gamma and the R. So I compare the two self-energies of the GW and the GW plus DMFT to understand what happens when we add the impurity self-energy on top of the GW. So we see that the main difference between the GW self-energy and GW plus DMFT self-energy is this very strong structure coming from the impurity self-energy that is kind of missing in GW. So actually GW self-energy also has structure like this, but at much higher energy. So it's kind of a spurious structure coming from the fact that the GW self-energy is not exact. So we have the same feature here for the R point. And this is the imaginary part of the self-energy. So this structure here comes from the peak structures in the imaginary part of the self-energy. So I have used, just to avoid confusion, I have used a time-ordered Green's function. So the imaginary part of the self-energy changes sign when we go from below to above the Fermi level, but this is just a convention. So usually this is plotted as positive here. So the thing I would like to mention here is that a normal LDA plus DMFT calculation usually uses a value of about 5.5 eV. So it's been pointed out actually quite some time ago that if we use this value, one could get the right band narrowing. But this large U then also gives large separations of the Hubbard bands. So it's of about the same order. Whereas experimentally, the separations within the Hubbard band is about 3.5 eV. So if we use a static value, one might get some inconsistency in the description of the spectral functions. So this is a comparison between this photo emission data and the calculated spectra. So we get, we think that these are correct positions for the lower and upper Hubbard bands within the GW plus DMFT scheme. And we also seem to get the correct band narrowing. So actually there have already been at least 2 calculations of the system. Here is the calculations by the group of Zilke. I'm actually involved also in this calculation. And there is also another work from the Karsten Hell's group. I think it has been published now in the Physical Review. So let me just show last slide maybe. So here I would like to show you the vertex corrections beyond the GW self-energy. So what we have done here is simply to take the difference between the DMFT self-energy and the corresponding self-energy within the GW approximations. And the difference then gives the corrections, the vertex corrections on top of the GW self-energy. So basically it gives this structure at a lower energy that gives rise then to the lower and the upper Hubbard bands. So since my time is a bit already up, let me just give a summary of the talk. So I would like to say that non-local self-energy tends to widen the bandwidth, and dynamic U enhances correlation effects in the sense that it gives a smaller Z factor compared to what you have when you use a static U. And we found that there is some kind of cancellations between the K and the frequency dependent of the self-energy. And so far we have quite a promising result for strength infinite, and we think that we should try this scheme for many other systems before making conclusions. So let me stop here.
Are there questions, comments? Vijay.
So can you write down some simple expression for U of omega, that some simple phenomenological, some kind of expression for that, so that one can try to do some simpler analytical calculations with that?
Yeah, so basically you just have if you make for example, a plasma on pole approximation, then you get the 1 upon omega minus omega p. That will be the simplest. Yeah. Okay, so you have something like, you have some weight here, yeah? Omega minus omega plasma. This will be your screening. So we are here. So your W is of course, there is the plus I that think about. But actually, if you look back at this picture here, it is not always so simple. In this case, there is a nice plasma peak. But already in this system, you can find some fine structures that why you have a narrowing of the bandwidth. So this because okay. So in the you get basically the following. So the real part of the self-energy. So I'm just looking at the correlation part. So this can be 1.5 like this. Imaginary part sigma. Now, if you have a static U, then this imaginary part of the self-energy is essentially confined to, you have a figure like this, and maybe it decays after some energy scale of approximately, I don't know, maybe 2U. So, but if you use a frequency-dependent U, the self-energy actually grows. So it doesn't go decays like this, it grows to very high energy. So this part of the spectra then gives an additional renormalization effect. So if you look at the real part of the self-energy, you get a, let's say, statement like this when you have a static U. So I'm just looking at the self-energy around the Fermi level. But if you include the dynamic U, there's a much steeper curve coming from the fact that you have a much more weight in the imaginary part of the self-energy. That's the origin of that.
Yeah, actually, I would like to make a comment just to complement what Ferdi is saying to this question, because you could view this in a completely different language. If you say that you can view it as electrons coupling to the plasmons, so it's a coupled fermion boson problem. You diagonalize that, you get to something which resembles to polarons, and then they have a polaronic mass.
there further questions or comments? If that is not the case, let's thank Ferdy once again.